Welcome everyone. I am happy to be invited here and to present to you part of my work that I did in my PhD, and together with some extra work that together with Kaspar Vereide we've been doing afterward. So today I'm going to present to you the topic of upgrading of hydropower plants to pump storage plants from a tunnel system hydraulics point of view. This work have been done, as Emily mentioned, under HydroCen, under the guidance of Professor Livia from NTNU, Professor Kaspar Vereide from NTNU as well, and Professor Michel Cervantes from Luleå Technical University. Just to give you a little bit of perspective, in HydroCen, we are divided into 4 different work packages. We have hydropower structures, turbines and generators. We have power market and environmental work package. And my work have been done under the first work package, hydropower structures. In today's presentation, I'm going to start talking to you a bit about the scope of our work, introduce to you what we've been doing, how and what information we also collected by reviewing existing hydropower pump storage plant projects in Norway. Further, I'm going to talk to you about a case study that we've selected and analyzed in detail, together with what tunnel reconstruction alternatives we could find. And I'm going to close this presentation with a short and economic analysis before some conclusions. If we look at the general power market, the continuously developing energy system, we can see that there is an increased share of renewable energy, such as wind and solar, and this has been going and it's still going to happen in the future. And as a result, we need more and more energy balance because these sources, these renewable sources, which I've been mentioning, wind and solar, they are volatile energy sources. Norway has a lot of hydropower, and in terms it is, which in terms is very flexible and renewable in the same time. And that has a big advantage. Considering that the need for storage is arising, batteries can actually provide short-term energy storage, but we also need to have long-term energy storage, weekly, monthly, or seasonal energy storage, for example. And this can be provided by pump storage plants as one alternative. Despite all this, building new large hydropower plants or new large pump storage plants is not really seen as a desirable option for multiple points of view, from environmental reasons, for social reasons, for economic reasons as well. But for all this, 3 downfalls, let's call them, there are one technical solution that we've been working for in the many years that we started. I think it's like 6 years, if I remember, in total. And that would be reconstructing already existing hydropower plants to pump storage plants. This forming the main scope of our work, namely enabling such reconstruction, such upgrades, and in the same time maintaining a stable hydraulic system after the upgrade. It has been shown in literature that such type of upgrades would have a capex reduction between 7 to 15 times. First and foremost, what we needed to do in our work was to identify what challenges can stay in the way of obtaining the stable hydraulic system that we wanted to obtain. And for this, we noticed that there are several, such as reversed head loss due to the reversed flow, mass oscillations amplitude, mass oscillation stability, and water hammer. But in principle, we focused our work on the first 3. Finally, we wanted to propose some solutions in terms of reconstructions, either of the tunnel system or of the surge tanks, depending on where we would find the need. So if we look at the challenges, first and foremost, if we look at just running an existing hydropower plant in steady state, we take just a general classic hydropower plant with water flowing from the upper reservoir along the head race tunnel and the penstock, taking it to the turbine, and further leaving through tail race tunnel and going to the lower reservoir. In order to have it in a classic Norwegian hydropower and hydropower point of view, we also equipped it with an upstream surge tank and a downstream surge tank. If we run this system in turbine mode, then we would have the hydraulic grade line as we can see here. And this is how the tunnel system have been designed for, in order to accommodate for any kind of limit operations that would go in turbine mode. If we simply would replace the turbine with a reversible pump turbine, then the hydraulic grade line would change to the pump mode hydraulic grade line, the green one that we see in this drawing. And already from here, problems can encounter with possible under pressure or lack of pressure at the reversible pump turbine inlet. If we look at the same system from a transient state point of view, the surge tanks have been designed in order to accommodate for any kind of mass oscillations that would encounter in the system while running turbining operations. If we take the same system and we move it to pumping, so what I've been talking earlier about just replacing the turbine without changing anything in the tunnel itself or in the surge tanks itself, then we would simply have a shift of the mass oscillations in upper or lower depending on the operating point that we are working with. And for upper, for example, I'm just going to laser here. So for mass oscillations in the upstream surge tank, what would happen in this case is that they would shift upwards, and then we can risk that if we don't redesign the upstream surge tanks, we would have overflow and resulting into flooding in the area. A similar case is for the downstream surge tank or for the tail race surge tank, in which in case of shifting of the water level lower than the design water level, then we would have possible air entrainment in the tunnel system. And this can lead to further risks and problems within our system. For us, in order to be able to analyze all this, what we decided is that we wanted to create a knowledge base in terms of having a technical review of existing pump storage plants in Norway. For this, we collected information about electrical equipment, mechanical equipment, power production, civil works, operational procedure, but most important, what we collected information about is challenges and technical solutions that have already been implemented or faced by power plant owners and power plant operators. All this information are actually gathered into a paper which is freely available online for anyone that wants to read it. But most important, what we could get out of this is that from all the information, we could calculate the specific cost. And we noticed that the specific cost is decreasing with the increase of head, as well as the specific cost decreasing with the increase of the upper reservoir, the size of the upper reservoir. And this, despite the fact that we only have 10 data points, because we only have, at the moment, 10 built pump storage plants in Norway, the trend is clear and promising. For this reason, we decided to take our study further and select a prototype for further investigations. In terms of tunnel system reconstruction alternatives, there can be mainly two alternatives. If you look at the first one, which would be building a new unit, either a pump unit or an RPT unit, reversible pump turbine unit, there would be certain advantages, such as having a low outage time, as well as having unconfined space for our turbine or for our pump as well. But there are also some disadvantages, such as the cost of the new or the extension of the powerhouse, as well as building a new pressure shaft or draft tube. Another part that another alternative is to replace the existing unit, what I've been showing you earlier in the drawing, to replace the existing unit with a reversible pump turbine. And such replacement has the advantage of a low civil work cost due to using already existing infrastructure, but at the same time, this also gives disadvantages because we would have a confined space for our reversible pump turbine, and there would be also that would result also in possible turbine capacity reduction, and on top of all of this, the high outage time is another disadvantage. This outage time actually can be overcome by synchronizing this work with major upgrades of hydropower plants. In general, hydropower plants tend to have a lifetime of, or not a lifetime, but tend to need a major upgrade or major reconstruction at around 50 years of age, 50, 70, something there. And that is exactly how old most of our power plants are, or many of our power plants are. So this way, if we would couple our upgrade with a major reconstruction that is anyway necessary, we could decrease the outage time. But independent of which alternative we are going, either having a new pump or replacing the existing unit with a reversible pump turbine, we would still need to have the reconstruction of the surge tanks and the sand traps due to the new flow direction and also the new limit operations that the system would be subject to. So from all this together, we could select our prototype, and the selected prototype in our case was Roskrepp hydropower plant for multiple reasons. Some such as having a high head design, which is a common design around in Scandinavian mountain range. Also having a long tunnel system, which is 4.3 kilometers. Another advantage or another reason for selecting Roskrepp hydropower plant is that we have a large upper reservoir, and also it being the highest in the scheme in order for allowing us to do measurements without being confined by other hydropower plants in the region. But most important, the reason why we selected Roskrepp hydropower plant is that it has multiple surge shafts, 2 along the head race and 2 along the tail race. So we would have an upstream surge tank right before the penstock. Then we have a brook intake as well, which takes water from a side catchment to the main head race tunnel. Then we would have a downstream surge tank and an unplugged edit. The downstream surge tank is actually connected through access tunnels directly to the powerhouse. And the reason why we also wanted to look at the edit is because there is a special thing about it. The inlet in the edit, or the entrance to the edit, is between the higher regulated water level and the lowest regulated water level on the lower reservoir, which means that when the water level in the lower reservoir is high, the edit is filled up with water, and it acts as an increased size of the tail race tunnel. But when the water level is low, the edit is actually behaving as a secondary surge tank along the tail race tunnel. So after we selected our prototype, we did further investigations. We did hydraulic measurements within our system. We did a tunnel inspection as well when the tunnel was dewatered. And one more thing that we did, and that was very crucial for our work, was that we got a 3D scan of the head race tunnel, the powerhouse, and some other components around. And what we found out from our 3D scan is that there could be significant differences between the construction drawings that we were provided at the beginning and the actual size of the components along the head race tunnel. This is important because it is the case for most of the most old hydropower plants in which the construction drawings don't match with a site. This is, as you might know, because of certain limitations or certain rules that are imposed by the constructor, by the developer to the constructor. But the important part for us in here is that one component, namely the brook intake, had significant differences. In our construction drawings, we could see a slope of 1 to 8.4. But from our 3D scan, we could find that the slope is actually 1 to 8.7. Another difference that we found in the brook intake is that our cross-section in the construction drawing was 8 square meters. But in reality, on average, the cross-section was 12 square meters. And from these two together, what we found out is that despite the fact that we thought that our brook intake has a water table cross-section area of 69 square meters, in fact, it was 112, which is almost double. It's 40% larger. And that would influence significantly how our system behaves in terms of mass oscillation. And then it would also influence how accurate we could simulate, or we could do experiments in terms of this. So one thing that I would like you to remember is that when we have an old hydropower plant, it is important to have measurements, if not even better, have a 3D scan in order to have the correct design and the real on-site design of the tunnel system. So with all this information together, what we did further is that we went into the lab, we built our hydraulic hydraulic system, hydraulic model, and then that one we used for analyzing how the mass oscillations would behave into the 4 shafts that we were having along. So namely the upstream surge tank, the downstream surge tank, the unplugged edit along the tail race tunnel, as well as the brook intake. With all this in mind, we ran also our model for the worst operating conditions in order to determine what types of limitations can encounter within this shaft from a mass oscillations point of view. And here we are looking at the one example of limit operation. What we did in this example is that we are starting from a shutdown power plant, so we have the discharge 0 cubic meters per second. Then we would start a pumping mode to full load. But afterwards, we consider that a pump trip would happen and the guide lanes would be blocked. So the water would automatically start flowing in the opposite direction and go into turbine mode. All the shafts behaved okay, and we were not having any limitations in any of them except for the downstream surge tank. And as you can see, the water level variation in the downstream surge tank goes above the overflow weir, which means that the water in our case would just spill out of the downstream surge tank and further into the powerhouse. If you remember, I was showing you earlier the design of our prototype. Well, if we look further or closer to the surge tank, what I said earlier to you is that the downstream surge tank is connected through access tunnel to the powerhouse. So it means that when the water would actually spill out of our surge tank, it would go directly into a powerhouse and it would flood the generator and further the turbine and everything in there. So for that reason, we needed to find alternatives in order to still be able to operate in pumping mode and avoid such a risk. And we came up with 2 different alternatives. One of them being surge tank, a differential surge tank. So we kept the size of the original surge tank, and we calculated a riser that we could include in our surge tank in order to accommodate for this this overflow and maintain the water level within the limits. Another design that we came up with was including expansion chambers. both for the upper part and for the lower part of the surge tank, and this coming from different operating points. From the operating condition that I showed you here earlier with pump trip with blocked guide vanes, we needed just the upper chamber, but the lower chamber was designed also due to the needs coming from other operating limitations. One of this, so the expansion chamber, the surge tank with 2 expansion chambers, we also built it and checked it from a hydraulic system point of view in the lab, and we found out that for the same operating conditions that I showed you earlier, we can see here we have the absolute same conditions. The water level in the surge tank does not go above the overflow weir anymore, so the water is confined within the correct dimensions of the surge tank, and the risk of flooding of the powerhouse is not there anymore. What we also looked into a little bit was a rough economic analysis, and what we found out in here, we look at 4 different alternatives. First, it would be the rehabilitation that I was talking to you about. Remember earlier I was talking about the fact that around 50, 70 years of age, any hydropower plant would need to go through a rehabilitation. And for this rehabilitation, we could calculate a project estimate of somewhere between 12 and 15 million euros. If on top of this rehabilitation, we would rebuild the existing unit, so we would replace the existing turbine with a reversible pump turbine and rebuild, do any other civil works necessary, our cost would increase to 30 to 35 million euros, having a marginal investment of 15 to 20 million euros. Another alternative that we looked into is the rehabilitation coupled together with having a new unit, a new reversible pump turbine unit of the same capacity of our turbine at the moment, 50 megawatt. And for that, the project would be estimated between 55 to 65 million euros, representing a marginal investment of somewhere between 40 and 55. But the most important component in here is that if we look at simply building the same system from scratch, so building a new pump storage plant with a reversible pump turbine of 50 megawatt, considering that there is nothing already built in the area or reused, we would have a project estimate or investment cost of between 230 and 250 million euros. So comparing to this cost, actually, a rehabilitation together with a new reversible pump turbine would actually represent just 26% of our cost. And if we don't have a new unit, but we are only rebuilding the existing unit, the cost would actually be reduced to 14% of the cost of having just a new project. So in conclusion, I want to say that it is actually possible from a technical point of view to upgrade existing hydropower plants to pump storage plants. And there are already available technical solutions, and there can still be technical solutions further developed. Many of them can be found within the review that I mentioned to you earlier, and some of them we also implemented in our model and found out to be successful. The cost of upgrading an existing hydropower plant to a pump storage plant can go down to only 14% of the cost of having a new project of the exact same capacity. And then what I also want to mention is that the capex is coming from literature is that the capex, the capital of expenditure would actually be reduced between 17 to 15 times if we go for an upgrade rather than going for building an entirely new system. Thank you for listening to me, and if you have any questions, I'm more than happy to answer.
Thank you, Livia, for your presentation. Are there any questions? Yes. Sander, you have a question? We can't hear you. Do you have your microphone on your head?
Okay. Is it better now?
Yes.
Yeah.
Yes, okay, yeah. I guess all of us have encountered that. Okay, I start again. Thanks for the very good presentation, Livia, and very interesting work. I was wondering, in the context of this, if you have been evaluating or been in contact with regulation authorities on, say, what is also the potential, say, for, say, on concession or, say, getting, say, the permits to do this. Is that easier if you kind of do it on an existing plant rather than doing more completely new asset, or say rebuilding it more like the new tunnel and such?
I personally have not been through my work because my work was mainly technical. But what I know is that at the moment, Roskrepp hydropower plant is actually in the process of being upgraded. So they are going to have the concession and everything. They are doing analysis, economic analysis on it, and going through the process. So we expect that in a few years, this is actually going to be implemented. And another thing that I would like to mention is that despite the fact that I was not in contact with authorities and I did not personally have this information, if we think from an environmental point of view, we don't affect the environment almost at all, comparing to just building a new project and just damming a new river. From a social point of view, people would all the time when you go with a new project, you would face some kind of can't find the right word right now, but you would face some kind of not people in the area not being so welcoming. And then when you upgrade the system, everything is already in place. So what you are reconstructing is within the mountain. You're just reconstructing the surge tanks. You're just reconstructing parts of the powerhouse. So they're not affecting the area either. I'm not sure if that answered your question.
Yeah. Just as a side, as a also reflection from my side, I think like the technical infrastructure as such is probably not the main issue, but potentially if you kind of want to also change the regulation of the reservoir, say utilize more of the say go increase the reservoirs or kind of increase the ramping speed is but I understand like if that has not been, say, core of your work.
No, that has not been the core of my work. And if we look at what's the name, the large hydropower plants, in principle, they tend to already have these regulations in place. And another aspect is that if, for example, we are also pumping and turbining, not only turbining, during the summer, we would be able to maintain our water levels even higher. So then we would have smaller fluctuations rather than draining long and having long periods of just draining and refilling.
Thank you.
Thank you.
Siri Stockstedt, you had a question?
Yeah, Livia, thank you. It was a very clear and engaging presentation, so thank you for that. Along the same line as Gaute was asking, I understand that you and Kasper, you have started to map whether other hydropower owners could have cases where you could look at the potential for rebuilding old power plants or power plants into reversible pump storage plants with this booster pump idea. But have you also started to map the potential around in Norway totally? Where could or how big is the potential for rebuilding into reversible pump storage in Norway. Have you any idea of the potential?
I don't have personally any idea about that, but I know that the study is going further. So I think this is actually a project under development, and as soon as they're getting funds, they're going to look more into this. But at the moment, no, I didn't study this.
No, but you are in the process together with Kasper. Are you involved with it?
I know that they are doing it, and I'm thinking of getting involved with it, yes, but I'm not at the moment involved. No.
Yeah, very interesting. Thank you.
Thank you.
Are there any more questions? Yes, I see a raised hand. No, it was Siri. So please join with any question at all. It's very interesting to hear the conversation going. Yes, Gaute?
Not anybody else. I can take a new one. What are you going to study now, Livia? What is the next after this?
At the moment, I went kind of back to my first love, turbines. So I'm working with Flow Design Bureau, and now we are looking into mitigation of RVR, rotating vortex rope. So it's a bit different than what I've been doing in my PhD. But yeah, we want to look exactly what Siri is saying on the side. We are thinking of still going with this project because it is definitely interesting, and I think it's a very promising part to keep working on. So we are thinking of trying to see what other potential power plants are out there that can get such an upgrade, and what technical solutions they could come up with, because of course these differ from project to project and limitations differ from project to project. Yeah, just trying to look further into it at some point.
And we have Gaute, do you want to reply? No. So we have a question in the chat. Is there any possibility of upgrading of HPP to PSP for the powerhouse, which is housing Pelton turbines, and head is in between 500 meters to 1,000 meters?
We did not look actually at all into Pelton turbines. And one thing that I'm quickly thinking right now is that in order to pump, we would need submerged pumps. So I'm not sure if that would be a possibility at the moment, unless it would be like a separate unit in which it would be an RPT or a separate pump unit. But still keeping the Pelton design and pumping, that would be, yeah, maybe not possible. There should be other possibilities with like additional units.
Thank you for your answer, Livia. Any more questions? No. So thank you so much for your presentation. It was very interesting to hear. And I would like to take the moment to advertise for this series of God forskermorgen, or Good Morning Scientists. We will start with a new presentation in 2022, the first Friday in January, the 7th. And we will continue doing this series all the rest of 2022. So reserve the time in your calendar every Friday, the first Friday of the month.